Hello everyone, this will be my second take of the recap videos of chapter 2 and 3 because I realized that my first take, I think this webcam screen is not so big. So anyway, let's try this again. Chapter 2, okay? This video we're going to cover chapter 2 and the next video we're going to cover chapter 3. Chapter 2 is chapter 2 and 3 are foundation for chapter 4 and 5, okay, which is perfect gas and steam respectively. So in order to understand and solve the problems involving perfect gas and steam, we need to know what exactly is a thermodynamic system, as well as what are the relevant energy equations that we need to solve, okay, in order to solve the questions of steam and perfect gas. So for chapter 2, it is about thermodynamic systems. Okay, according to the notes, a system is defined as a collection of matter, okay, within a prescribed boundary. So what you're going to have is something like this. Okay, this system is found within the dotted lines that is called the boundary. Okay, and within the system is what will be called the working fluid. Okay, it can be a gas, can be air, can be oil, can be water. Okay, depending on what kind of system you're looking at. And the boundary is the limit of where the mass of this collection will be. Okay, anything that's outside the boundary is called the surroundings, which will not be very concerned with the properties at the surroundings. Okay, so there are two types of systems. Okay, closed and open. The key difference is that in closed systems, your fluid mass will not go through the boundary. So, for example, if we look at a cylinder, right, with a piston. So this piston is here. So what is the fluid? The fluid can be air, okay, which is found inside the cylinder. So this is your fluid, and this is the so-called system. Okay, and the boundary is a limit that encloses the air. Okay, whatever outside is called the surroundings. Okay, this piston can move up and down, right? So as your piston moves up and down, so supposedly it moves down. Okay, this air is going to be compressed because the volume decreases from bigger volume to smaller volume. Is it going to compress? And the closed system can now be defined this way. Okay, so you realize that there is actually the air does not go out across the boundary. So this is called a closed system. But if you compare to open systems, right? For example, any open system, okay, you typically see an inlet going in and an outlet. And what goes in and what comes out is a certain gas, a certain fluid, okay, or a certain liquid or such. And then your boundary will then be this magma in this manner. And whatever that you are calculating, whatever properties that you want to know, will be the properties of the incoming and outgoing fluid that is inside. Okay? And within this system, something will happen. Either it will gain heat, or it will do work, or things like that. Okay, and that is what chapter 3 will be about. Okay, so open systems in particular, there are three different types of open systems that this module will be concerned with. Okay, the first one will be pumps and turbines. Okay, pumps and turbines looks something like that. Okay, you are going to have a certain fluid coming in, and then you're going to have rotating blades that will force the fluid that goes in, right, to go out in another channel. Okay, if you look at the other cross section, then this will be then the fluid will actually come out from here. Okay, so the main difference between pumps and turbine is this: the pump will actually provide the energy to the fluid. Okay, means when the fluid comes in, it is actually at a lower energy state, and that is where it will get pushed by the pump blades and exit in a higher energy state. Okay, so actually work is done on the pump, on the fluid. For turbines, the fluid come in with a higher energy state, and instead of being pushed by the blades, it will itself push the turbine blades, okay, to generate work. And in that case, right, the shaft will get turned by the fluid. All right, so the fluid is actually doing work in the turbine itself. So that is the main difference. Okay, the next type of open system will be boilers and condensers. Okay, so as an example of boilers and condensers will look like this, whereby this is a kind of a boiler. The boiling liquid will come in somewhere and then exit in the other way, but not before it gains heat from a heat source. Okay, for a condenser, a high temperature fluid will come in and it gets cooled down, okay, by a colder liquid, okay, and then you come out in a lower temperature. So boilers and condensers, the idea is basically an exchange of heat between two kinds of fluids. Okay, so that is the idea. And the third kind is nozzles and diffuser. Okay, nozzles and diffusers diagrammatically looks like this. Okay, the key thing is to speed up or slow down the flow. For a nozzle, we learned before, due to conservation of mass, the flow speed at the outlet will increase. Okay, but for the diffuser, as it reaches the outlet, it will slow down the flow. Okay, and you can see that the boundary can be drawn in this way for these two systems. Okay, so the question is that what do we want to know about the system? Okay, what do you want to know about the system? Well, we want to know things like pressure, temperature, right, volume, and its own internal energy, and as it goes through the system, what kind of work is being done, or what kind of heat is being transferred. Is it gaining heat or is it losing heat? So these are all the things that it is of concern, okay, when we look at thermodynamic systems. And if we look at these are actually properties of the fluid. Okay, properties that are inherent with the fluid, and they will change when from the beginning to the end, from the inlet to the outlet. These properties will actually change. Okay, and just to draw an analogy, if you have done your three-dimensional coordinate system before, this is x, this is y, this is z, right? So with a certain x, with a certain y, with a certain z, what do you get? You will get a point, right? So so these three axes will form a point over here. So using the same theory, if you, instead of x, y, z, you get P, V, T, okay, at a certain pressure, at a certain volume, at a certain temperature, what do you get? You are going to get what we call a state. Okay, so a state is where where the fluid is currently existing as. Okay, so we will always talk about initial and final state, right? For closed system, we imagine the piston. Initially the volume is this big, then after that it gets pushed, right? Then the volume is actually smaller. So there is a change in volume. We call this a change in state. Okay, so there is an initial state, and then there's a final state. Okay, likewise, right, for these systems, open system, there is an inlet state. So as the fluid comes in, there it has a certain pressure, volume, temperature, and as it goes out, it has another state, outlet state. Okay, so if 1 is defined as initial or inlet, 2 is defined as final or outlet, and you are going to have this. Okay, you are going to have an inlet state and an outlet state, an initial state and a final state, right? So from here to here, so that is the process going from the uncompressed to compressed. You're going to go from state 1 to state 2. Okay, from state 1 to state 2, 2 points form a line, right? It's the same as your coordinate system. 2 points form a line, and this line, we call it the process. Okay, in thermodynamic terms, this line is called the process. It is from state 1 to state 2. Okay, so this is the whole idea that will be covered in chapter 4 and 5. Okay, you're always going to have a beginning and an end. Okay, and you're supposed to identify the process. Okay, what happens during this process will be the work that is being done or that will be done, or the heat that will be transferred, either loss or gain. That we will need to find out. Okay, so this is the whole idea of chapter 2. And in the notes, you will see the last few parts, there will be mention about different kinds of properties that are important to this module, mainly volume, mass, density, pressure, specific volume, temperatures, things like that. Okay, and we're going to introduce a type of energy called the enthalpy, which is the internal energy. We know U is the internal energy. Okay, so energy, right, naturally is in joules. Okay, so internal energy, so enthalpy is represented by H, is internal energy plus pressure times volume. Okay, so this is enthalpy. And in the last section, we talk about specific properties. Every time you see the word specific, okay, you need to straight away relate it to a per kilogram basis, meaning that whatever properties that you're looking at, you divide by the mass of the system. Okay, so imagine I have a container of 1 kilogram of air. No, okay, let's say it's 2 kilogram of air. So mass is 2 kilogram, right? So if internal energy is 100 joules, then my specific internal energy, represented by small letter u, is big divided by mass. Okay, that will be 100 divided by 2, which is 50 joules. The unit will not be joules, but will be joules per kilogram. Okay, same applies to enthalpy. Okay, in fact, same applies to specific volume, which you have been taught before. So this will be what? Meter cube per kilogram, and this will also be joules per kilogram. Okay, so we're going to talk more about the conservation of energy, but for now this will be the summary for chapter 2.